So I'm going to talk about Vertex-CFD that we have been developing at Oak Ridge National Laboratory for almost 3 years now. The objective of this project is to develop a CFD solver that we can run on GPU platform, but also CPU platform to model fusion blanket problem. So Vertex-CFD includes different projects. We have multi-phase application, radiation, a vertex closure that is focusing more on artificial intelligence and machine learning model. And we also have some adaptive mesh refinement capabilities that we are also developing. What is important is for this community is Vertex-CFD is based, relying on Trilinos open source package, and we use Kokkos as well as part of Trilinos and mostly Panzer. So, like I said, the application problem, the targeted application problem is a fusion blanket problem. So this slide is just to showcase all of the different physics that we have been implementing in the code in order to solve this complex 3D problem. So there is fluid equation, heat transfer, MHD, and we also have turbulence models. Some capabilities are still under development, like conjugate heat transfer. So here we're talking about multi-region capabilities so that you can solve with solid and fluid regions in contact. But again, the application problem is fusion blanket on GPU using GPU platforms. And so we've been running the code on Frontier and also some other HPC platform like Perlmutter or Summit that are NVIDIA GPUs. Recently, we added 2 new capabilities that are TensorFlow Lite for machine learning capabilities and also ArborX, mostly to be able to interpolate magnetic field that are predicted from external packages. This project has a very high focus on machine learning capabilities so that we can close the gap that are found in the physics. So when you do MHD with fluid equation, the MHD effect are going to strongly modify the fluid behavior that you commonly see in other application problem. And so because of that specific MHD effect, we use machine learning in order to modify some of the closure models that we use in other application problems. So the challenges that we faced over the past year when we started to deploy the code on Summit and Frontier. So Summit was an NVIDIA GPU platform, and Frontier is AMD. One thing that we noticed is we had to change actually most of the files because of a requirement of the Kokkos heap backend. So the Kokkos inline function annotation was required for the code to compile on Frontier. The other challenge that we faced was related to the memory allocation. That one was a big one. I think we're going to have to modify probably up to 50% to 60% of the source code in order to be able to effectively run on Frontier. So the main issue, not the main issue, but the approach that we have been following with Vertex-CFD is we build the Jacobian matrix using automated differentiation. And when you do that, you rely on the Saccado package that is going to numerically calculate the derivative with respect to the degree of freedom you're solving for. So when you do that, it's very simple because you don't have to derive by hand the Jacobian matrix, but it has a cost. And for example, when we evaluate the preconditioners of the Jacobian matrix, it can account up to 40% of the total world time. So it's quite large. So the issue that is related to the memory allocation is related to the way that we're building the equation, we're building the residual. So if you think of the temperature equation when you have a convection term and a diffusion term, the way you implement that in Panzer is you build a closure model that is going to implement the convection equation. When you do that, that same closure model is used, 1, to calculate the residual, and 2, to evaluate the Jacobian matrix. When you evaluate the residual, the scalar type is a double. So the scalar type is just a a type that is used for temporary variable inside your closure model. So if you do a residual, it's defined as a double, but if you do a Jacobian evaluation, that scalar type becomes an AD type, so automatic differentiation type. That was causing issue on the GPUs because you have a lot of allocation, like local memory allocation that were saturated the GPU memory. So that issue only showed up on 3D meshes. We were testing a lot the code on CPUs and GPU using 2D meshes. And over the past year, when we started to test the code on 3D meshes, that's when we started to see that issue. So the way we fix that issue is, one, to pre-allocate the memory using scratch view, so before we enter the parallel 4, and two, do some, rely on universal reference auto so that we can use this pre-allocated memory variables. So by doing that, we were able to demonstrate that the code can scale on Frontier. So those plots were generated a few weeks ago. And before those fixes, we could only fit like a very small mesh on each GPU node. So we were doing like a mesh of 8 by 8 by 8, which is very small. And now we can fit a mesh that is about 1,000 times bigger. So the strong scaling and weak scaling look OK. And we're doing some additional testing in order to evaluate the performance of the code on larger meshes. Another thing is related to the work set size. So Panzer has an interesting way of dealing with meshes. So you decompose the mesh on cores, but then Panzer will do a sub-decomposition based on the work set. So a core can contain multiple work sets. And the work set size is something that can be defined in the input file. In theory, it's architecture dependent. So if you run on CPUs, the work set size is going to be of a few hundred mesh elements. But if you're on GPUs, if you want to see good performances, you want to have this work set size of the order of a few thousands. So we run a few tests on Frontier by varying the work set size from like a few hundred to 4,000. And so you can see the change in performance. We can get a speed-up increase of up to 50% when we use a few hundred mesh elements per box set size. I think the takeaway of this talk is memory optimization was key for us to effectively run the code on GPUs. I'm now pushing my developers to do more code development on GPUs because we've been using CPUs a lot, and being able to CPUs is a lot more forgivable. So you really want to, I think, test and develop as much as you can on GPUs. And the preconditioner, building the Jacobian matrix, is still the bottleneck for us. So we are investigating other avenues in order to reduce this the intensive memory task by looking at a physics-based preconditioner, for example. Any questions?
Thank you. We have time for a question or so while we are getting switched over. By the way, Julian, I think your adapter does improve the stability of the interface. Yep, Mark.
Yeah, just asking quick, have you considered having a work set per team instead of one work set for the entire kernel? Or is that kind of tied to the Panzer architecture?
So I don't know if we can do that. I think it's a one work set per simulation. So you have to allocate the work set before you run.